Hello everyone, I'm Vidram Landis presenting you the project Quantegrity, a quantum enhanced e-voting system. My teammates are Diniti Karmadas and Lisa Disanayak. We were guided by Dr. Asanka Sarkar. Current e-voting systems have several problems. First, they are vulnerable to quantum attacks. Second, they often act as black boxes where voters cannot verify their vote. So, we need a system that solves the security issues and the algorithmic transparency. Our solution Quantegrity uses a novel QKD protocol to secure the transmission of data and vote authentication. We also use confirmation codes to ensure that voters can verify their vote wasn't tampered. The architecture consists of three main pillars. The voter and election authority exchange keys via a quantum channel. Once the voter is authenticated, the vote is encrypted and sent to a separate voting server, which uses a mixnet to shuffle and tally votes. Our core quantum technology is based on a brand new entanglement-based QKD protocol called SEDJO. This can also be used as an authentication protocol. For the voting mechanism, we implement the Quantegrity system. This gives every voter a unique confirmation code. If that code appears on the public bulletin board, they know their vote was counted. Our main focus for the project was on improving the security of the SEDJO protocol and applying error correction, while also making the system a feasible solution to run on NISC systems. So, with some inspiration from BB84 protocol, we implemented several strategies. So, what we are trying to do with this protocol is to create a perfect copy of a secret key in two places. As the name suggests, this is an entanglement based protocol and therefore requires entangled qubit pairs. Alice and Bob will get their pairs from an entanglement provider, which should be a common scenario once quantum networks are realized. Since we can control quantum networks with Qiskit, what we have done here is basically combining the circuits of both Alice and Bob into a single quantum circuit. The first step that both Alice and Bob do is preparing their auxiliary qubit. Then they will use the Duchess oracle function to encode their secret keys into the circuit. Once they have encoded their keys, both will measure their circuits, collapsing the entangled state. Let's assume that Alice's key was 1010 and Bob's key was 1100. In this case, the measurement probabilities consist of unique combinations of two 4-bit strings. In any given scenario, we would only observe one out of these 16 possibilities. So, for the next examples, we chose the marked measurement element. Going back to our key generation, after the measurement, Alice will announce her initial secret key in a public channel. Using Alice's secret key, Bob's own key and measurement, he can now derive what Alice's measurement is. Another interesting feature of the protocol is that if you encode the same keys on both oracles, both could observe the same measurement. So they can use it to authenticate themselves without revealing any keys. The downside is this method requires the control of multiple qubits at once. So to generate large enough keys, we had to use a segmented approach. In an ideal world, this would be as easy as we said, but we have noises and imperfections. In key generation, we can't say the key is 99.9% good, it just has to be perfect. This is also the place where our segmentation benefits us. We perform simple parity check on these segments. This is efficient and effective because we are only concerned about bit flips. We keep Alice's measurement as the gold standard. An interesting deviation from BB84's method is that we are not publicly announcing the parities. Instead, we use a single bell pair to encode the parities. In this case, the parity match or mismatch is preserved, but the actual revealed bit is random. If the parity matches, we can move to the next segment. However, if parity mismatches, we employ a binary search to find the error bit similar to the BB84 error correction. Once we have found the error, Bob can flip his bit to correct it, but Eve doesn't know what Bob has had in that bit. Once we have done this process to all the segments, we have a complete key. While our method is superior, there's still some information leakage. As a safeguard, we use a hash function to shrink our key, making any information an Eve may have useless. Now we move to our voting system. Step 1. Alice goes to a registration center and presents her ID and biometric data. Bob verifies Alice's identity and generates two keys, gold and silver. Bob encrypts the gold key using Alice's biometrics and stores it on her voter ID card and provides the silver key as well. At home, Alice initiates device verification to complete registration. Bob sends an OTP encrypted with silver key. Alice decrypts it and successfully validates her device. On election day, Alice logs into the voting platform. Bob initiates a QKD process, and they both input the gold key to create a platinum key. Bob then sends an OTP encrypted with the platinum key, which, if she decrypts, validates her identity because she had to decrypt the gold key with her biometrics. Bob initiates another QKD process, and both inputs platinum key to get a new diamond key. Bob redirects her to a secure voting server. The server encrypts a ballot ID using diamond key and sends it to Alice. Alice can choose to vote or spoil her ballot. If she chooses to spoil it, she receives all the confirmation codes in the ballot. If she chooses to vote, she can encrypt her chosen answer with diamond key and send it to the server, which replies with a confirmation code for future verification. By checkpoint 3, we managed to implement error correction, segmented key generation, and privacy amplification strategies to our QKD protocol, and also validated them with simulations. Our initial plan to implement was to implement a fully interactive demonstration where a user can experience the complete voting workflow. While we have implemented a nearly complete demonstration using the non-error corrected protocol, we are yet to fully integrate the enhanced protocol. Our immediate next step is to finalize the implementation of the complete demonstration flow and possibly make this a deployable solution integrated with real hardware. We also plan to further improve our protocols and run security benchmarks to stress test them and finally to publish our findings. We learned a lot from this project and enjoyed working together in such a niche area. We learned a lot about the challenges in developing realistic quantum applications. The thing that inspired us the most was learning about the simple yet elegant solutions people have made to solve really complex problems. So, thank you very much for your time.